Good morning, everyone. Today we're going to discuss with you about the problems that has combined for some across fields of engineering issues. It's called probing Wi-Fi problems in the publication transportation system, and it has been analyzed in a theoretical and also application models in implementation levels. So first, we want to introduce you some backgrounds or the terms for the problem. First, there is a problem for probing the quality of link state in TCP/IP or UDP between different genres of networks. If you are interested in all those groups of professional studies, you can check the network research laboratories in IIS of Seneca, which has been presented by Dr. Chen. When he was in UCLA, he has worked on the probing problems with different types of networks. Either Ethernet for the wired networks or wireless networks. Now, the wired networks, most of the challenges has been tested because if you just accidentally browse the websites for those wired networks, they are usually provided, even some websites that provided the quality test because they might have provided servers in big cities in different parts of the world. So you can just you can just use your sorry. So you can just use your browser and found the exact website and type your and choose the address of the servers and just one click away. Maybe after 30 minutes or 30 seconds or 1 minute, and then you can get the quality of the your connections from this website to the other website. But in here, we're also trying to tell you that the more challenging issues is in the Wi-Fi problem, especially in the public transportation system. This has been confronted by those users, especially the users who has traveled around the world, like backpackers. Usually, the issues that all those cell phone company has chosen uh, is that they provide 3G or 4G or maybe WiMAX. They do some WiMAX applications that has been experimented in Georgia for a while. But in here, we're going to introduce you the specific genres of problem, which is called, which is it from the Wi-Fi. We know that usually we can buy Wi-Fi routers and set up all those wireless connections inside of the house. And you can just easily connect it because once there's a little either the black box has been set up, then you can go anywhere but still just connect it very well. However, if you are just a visitor to a new country and you don't have the budget to pay for the whole month's paying service by a cell phone company in this newly visited countries. And what will be the problems for this? You might be able to use your laptop or your cell phone, trying to search for the signals of Wi-Fi. Especially, they do exist some, especially in big cities like capital cities and countries, they might provide the Wi-Fi connections for free. So this is our motivation. We have tried to test the Wi-Fi quality of service by probing in the Taipei public transportation system. And what is the issue that we have found? First, we have to test it that throughout all lines of the public transportation system. When will be the best way to probing the service? And we use the very simple method. You can just use the pin, or you can just use the trace route. All of those are engineering terms. If you're interested, you can just consulting any engineering friends that by your side. So for this issues is that usually we can easily find the maps of the public transportation system, but how do we measure the quality of the service of the Wi-Fi connections? We have to find that in bidirectional, right? Because the Wi-Fi connections, if you're coming from one direction, then going backwards, forwards, the quality of service might be different. So what does that mean? That means for one line, we might have to starting from the beginning, the first station to the last station, then go back from the last station to the first station. So that gives us a motivation for the traveling salesman problem. The applications of a traveling salesman problem. That is, you have to visit every station of the public transportation system, and especially for every lines. For example, green line, orange line, yellow line, blue line, purple line, brown line, whatever. And you have to probing uh, bi-directionally for every line. So what will be the best way to probing and provide the total quality of service report of the public transportation system and also the potential Wi-Fi problems that might have been provided by the capital city. And why do we mention the traveling salesman problem? Because traveling salesman problems by its original definition, it mentioned like the following. Suppose you are a traveling salesman and you would like to travel through a lot of different cities. Because every city you might be able to sell your goods and get profit from that. But also because you're traveling costs you a lot of fees, transportation fees, or maybe the lodging fees, and so on. So you have to be very, very economical. But however, since most of the salesmen, they might be greedy to visiting all his goal cities, so he has to figure out, or she has to figure out, the ways to visiting every city in the most efficient way. But unfortunately, in applied mathematics or computer science, this problem has been proved to be incomplete. That means this is very hard. If you have cities, if you want to find out the best application, maybe you can check when Mr. Barack Obama he was trying to find the campaign of his second term. He he does figure out a way to do the lecture traveling different states and also going back with the best way because we accidentally found that by the reports that he has a very good technical team for supporting his campaign. So this is some real-time large-scale application issues. But in this report, we're going to do that is by combining the probing problems and also the testing problems. That is, we're combining the theoretical issues and also the real application or implementation issues. And if you're interested in what kind of variations of the list problems, they do exist a lot of paper. If you just type in travel assessments in Amazon, they at least two or three books that has composite most of the problems and the variations and how the engineering trying to tackle them and provided feasible, infeasible solutions. And in this issues, we're going to introduce you some small reductions and usage for that. Because now the problems that we are facing in is you might just hop in, by reaching one accidental stop of a line of the public transportation system, and the first goal, you might have to probing starting from that, or and along the original line, or just trying to find another line that's near your stop, and so on. So how can you find the best solution so that your probing task could be finished in the most efficient way? Here we provided a reduction of it. This is some very simple reduction. What is the reduction that we have provided for this Wi-Fi problems in the public transportation system? First, we might have noticed the following issues. First, once you reach the line, then the most efficient issue is that, for example, if you reach a stop of the red line or a green line, then you might trying to stop with some place that can reach you to the beginning of this line. If it has been occupied by multiple lines, for example, like little five stations of the Mora of Atlanta, it has some different lines that has crossed that. So you might choose the nearest stops of the public transportation and reach that by the end of the terminal stations, either from the beginning of the line or the end of the line. So this makes sense because you have to figure out it from the start station to the end station and then backwards. So I think the first step this is very intuitive. The second step is that once we are given the maps of the public transportation system, is it possible that we can simplify the topology that of the maps that we are given? We might be able to do that by just taking away all those branches or tentacles that stretching out from by the stops that only has that belongs to one specific line. We might able to cut those specific lines because once you reach that specific branches of that line, you can only go one direction to the end of that line and then go backwards. So that means once you reach that stop, there is only one solution. And that part of solution is not an issue when the major challenge problems that we are facing in is the switching between different lines. So we can cut up all those lines when we figure out the problems. And once we cut up those branches of the maps of the public transportation system, what will happen? It will happen is that you can assume that every stop of the public transportation system is bi-connected. And since we know that they do exist very, very good solutions for the bi-connected maps, the traveling salesman problem applications in the bi-connected graphs. So you can easily consult the solutions, for example, some very beautiful theoretical work, which currently might have good works in real life application. And also you might be able to consulting Professor Michelangelo Quickney's previous work in Emory University. They do provided good solutions for those bi-connected graphs, the traveling salesman problems, and especially the very, very beautiful theoretical bound. So in this paper, if you're interested in the detail, you can consult both of these two authors' work. And if you're interested in helping the backpackers traveling by using the public transportation system, that has existed in most major capital cities of countries. Here we might provide you good solutions. So if you're interested in the details of what we were reported, we might be able to provide you later on with a technical report. This is very, very interesting and exciting combinations of theoretical and engineering issues, and maybe really applications for travelers, real travelers, not only for salesmen. So thanks for listening to this video, and hopefully we will give you a more detailed technical report soon. Thank you. Bye bye.